Hi, so I'm going to talk you through a Poisson regression, and this is the second version, giving you more fleshing out the details. Okay, so I've loaded the data. This is the data frame is called crime. Now, because it's a very long data file, we just list the first 5. Just look at the structure. So here you go. Alright, now the dependent variable is number of times a man is arrested in 1986 in a particular city. That variable here is called NR86, standing for number of arrests in 86. And we've got a whole pile of covariates and also indicator variables. Covariates are continuous, and the indicator variables, they are dummy variables. Indicator variables is coded 0 and 1. Alright, now just how large is my sample size, because that's something you'd like to know when you kind of reporting your stats. So use the lemp command here. We'll just look at the dependent variable, 2,725 observations. And that's a good reason why we didn't just type in crime, because then it would have just flooded our screen. Next question some of you might be thinking is, okay, well, you know what a Poisson is. We've learnt it in the first stats course we had. A random variable, say x is Poisson as a parameter lambda, and x then is the number of occurrences of an event in a given interval. Alright, so we're looking at counts. I'm going to look at the histogram to show you why it's not a good idea to pretend that your data, your dependent variable, is continuous and then just run the usual regression. Here it is. Clearly, most of the observations counts are bunched close to 0, and because it's highly skewed, and the numbers, the kind of values are also very limited. Alright, so it's not continuous. Cause remember, continuous normal, because remember, a normal distribution, those range of the interval values that x can take is from minus infinity to plus infinity. This is nothing like that. So it would not be a good idea to pretend that this is a continuous dependent variable. Okay, so that brings us on to the next question. Why do we want to build a model in the first place? Well, in this case, we want to build a model to explain the counts. So we want to build a model of conditional mean, right, and the focus on interpreting the coefficients. A thing with the Poisson we've learnt is that if x follows a Poisson with a parameter lambda, we know that for a Poisson the mean is equal to the variance. This is a condition that is, from experience reported by people, often not satisfied. Most often it appears that the variance is greater than the mean. We can have also that occasionally that the variance is less than the mean. Indeed, sometimes you can get the variance that is equal to the mean. Right, so to see an idea for this data, get an idea of this data, whether we have a violation of the assumption of the Poisson. Let's look at the mean of our dependent variable, and the variance is bigger, 0.73. So this suggests, because it's not a test, that we do not have the Poisson condition that the mean is equal to the variance. Specifically, since the model of a regression, that the conditional variance does not equal to the conditional mean. Where we have that the variance is greater than the mean, we have what is called overdispersion. And if the variance is less than the mean, we have a case of underdispersion. And if the variance is equal to the mean, then we have the condition for the Poisson regression. What's the implication for estimation anyway? We're going to estimate the model by MLE, and the implication is this, that if the Poisson condition is not satisfied, then MLE, maximum likelihood estimator, is still consistent, but the standard errors are wrong. So what we have to do then, if we have overdispersion or indeed underdispersion, is to use MLE but correct the standard errors. Okay, so putting it formally before we kind of look at the code, here is the assumption that the GLM assumption is that the conditional variance is equal to a constant which turns out to be sigma squared times the conditional mean. Now this guy here, the sigma square guy, if that is equal to 1, so it's pretend it's gone, then that means we have now that the conditional variance is equal to conditional mean. That means the assumption of Poisson is satisfied. Okay, but if the sigma is squared is greater than 1, or sigma greater than 1, that means we've got overdispersion, and if sigma squared is less than 1, as I said, we have underdispersion. Well, we'll start off with the usual Poisson model first. So we use the GLM command, dependent variable, till the whole load of covariance indicator function, and then we end it with family equal Poisson and tell it what the data is, its crime. Okay, by the way, all this code is on the website statisticsmentor.com. And we look at the summary. Okay, there you go. These are the estimates. We know. We look at the now. How do we know? We've already seen that with our possibility of overdispersion here. How else you can pick this up is here. Look at the residual deviance. That is like RSS. Look at the degree of freedom. Well, you know, if you take RSS divided by its degree of freedom, that's an estimate for sigma squared, isn't it? The variance. So if you this divided by this is obviously greater than 1, so that suggests overdispersion, because this sigma square turns out to be, where is it? Turns out to be this guy here, sigma square, in your GLM condition, that the conditional variance is equal to sigma square times expected value of the conditional expectation. So this here is not exactly it's not exactly equal to that sigma square, but it suggests that. Okay, so this divided by that is greater than 1, so that's over dispersion. So we know not to trust in these standard errors, although the estimates are fine. So instead, what we do now is we run the Quasi-MLE, which is basically running the MLE again, but only this time you correct the standard errors. Quasi, that's all you do. Oh, let's change this to R2. Okay, there you go. Let's look at this summary. R2. Here you go. Okay, we have like 2 regressions. We want to compare the estimates and the standard errors. It would be nice if we can get everything onto one table, so this is what I'm going to do now. We're going to extract the coefficients and the standard errors of each table and compile them to a new table, which is great for, much easier to see what's going on. Also good for when it comes to presentation. So we need this package called ARM. Let's load that. Right, then what I'm going to do is coef is a command that extracts the coefficient from my first regression. It's called C1. Coef extracts the coefficients from my second regression, which is from the Quasi-MLE. So there you go. So I'll call it that. Similarly for the standard errors, se.coef, and it's the se.coef that requires the ARM command, the ARM package. Sorry. Okay, so that's what we have. Enter. And now we bind all the stuff together. So we use the bind command there. This is a nice table. So here's our set of x's, let's say. First, this is from the first 2 columns are from the first regression. You're just using Poisson regression, and the second one is using the Quasi-Poisson MLE. We can see the estimates are identical, but the standard errors, they are different. Moreover, you can say more than that. You can say that consistently what you can see is that the standard errors of the Quasi-MLE greater than the standard errors. We're just running the Poisson. In fact, there is a relationship between this standard error, just from the normal Poisson regression, and the standard error from the Quasi-MLE, the robust method, because it's robust to the fact that the data is not exact, it's not Poisson. But first I want to look at the interpretation of the coefficients. And we just said that they give the same irrespective of whether we run the Poisson MLE or the Quasi-Poisson MLE. Right, we have a mixture of continuous covariates that are continuous and also indicator variables. I'm going to do a continuous x first. Let's use this one, which stands for average sentence of a person. of a criminal. Now it turns out this thing was not significant, but I don't care. Let's just kind of show you how to interpret it. Okay, if that's not significant means that it's not actually a predictor for the number of times arrested, but let's just ignore that for the fact. What you do with the this Poisson regression is you take the exponential of the number 2, 3, 7, 7, and that number gives you a factor increase or decrease depending on whether this number is less than 1 or bigger than 1. Gives you a factor increase or decrease on the number of times that the person is arrested compared to the original number of arrests if that variable goes up by 1 unit. So what this says, say the average sentence is in years, we would say that the model predicts that, all else being equal, i.e. holding all these other things fixed, that if the average sentence went up by 1 year, then the number of arrests in a year of a person would fall by about 2.4%. Okay, to do 1 minus that figure, because no, it's a decrease, it's a fall, so 65, and then multiply that figure by 100, so it's about 2.4% decrease. In other words, increase the sentence, the model predicts that fewer arrests will be made in that year, in a year. An example of interpreting a indicator, or otherwise known as a dummy variable, we've got ethnicity coming in this questionnaire, coming in 3 in this data. Sorry, it's not a questionnaire, it's a data file. In 3 types here, they've got white, black, and Hispanic. You see that the white is not here. We've only got black and Hispanic. These are indicator variables, so the black one means coded 1 if the person is black, 0. Otherwise, Hispanic is coded 1 if that person is Hispanic, at 0 otherwise. White has been left out. It is the baseline or reference category. Recall that for indicator variables, if we have k number of categories, we use k minus 1 dummies if we include the intercept, alright, which is the case here. And the interpretation of the coefficients, this compares the number of times arrested in the year 1986 of each of these kinds of ethnicities compared to white, the reference category. So let's do Hispanic. We take the exponential, just do the same thing again, 0.499, 4998. Okay, this time we get a number exceeding 1, so it's an increase. It's an increase relative to white person. What this says is that the model predicts about 65% higher number of arrests made for a Hispanic person compared to a white man, with all other variables held fixed. Right. Now, some of your lecturers, I've done this using the exact method, but what you might have heard, so I'll just mention it now, is that some of your lecturers might just say, oh, just times the coefficient by 100 and that'll give you the approximate change, which is correct if those changes are small. So if we go back to average sentence here, that figure was a fall of 0.023. So if you multiply by 100, that gives you about a percentage change of 2.4%. Well, that's what we came here, 2.4. And those numbers are very similar because that change is small. But if we look at, and that approximation works well when these numbers are small, but if they're not, then there's difference. So for example, Hispanic, 0.49. So if you're following that rule of times by 100, you'd say about 50%. But in actual fact, we've got 65%, so that's a difference of 15%. So if you just know that, just to use this exponential, that's just better. Okay, so that's the coefficients done. Now I want to talk more about the standard errors. This in relationship to this. Basically, this guy here is obtained by taking this standard error and multiplying it by the overdispersion parameter, that parameter measuring overdispersion or underdispersion. Okay, so if we just take this guy and divide by this guy, just to get an idea of what that number is, 0.828 divided by 0.067, we get 1.2, about 0.1 1.24. So that's about what the factor difference is, and that comes about because the GLM is assuming that the conditional variance is equal to this dispersion parameter multiplied by the conditional mean. Right, that's why I'm looking at the factor here change. So basically, this is like the dispersion parameter, and it's bigger than 1. So that's, and it's bigger than 1, so it means that we've got over dispersion. And so I say again, standard error here is equal to this standard error multiplied by your, this is sigma, right? My absolute value of the square root of sigma square. So how do I get this 1.23? Clearly it is not the 1.23 when we look at, it's not this divided by that and take the square root. It's not that, is it? So if we do 2, it's not the residual deviance divided by its degrees of freedom and then the square root of that. 1.039. Okay, it's not that. So I'm going to show you where it comes from, the number 1.23. The estimate of that sigma square is we actually require the standardized residuals, not the deviance, right? There's kind of differences in these types of residuals when it comes to GLMs. So the kind of residual I'm looking at here is the Poisson's residual, otherwise known as the standardized residuals that you've come across in standard regression, which is, if I bring it up here, all these notes are going to be on the website, by the way. So scribbled it down earlier. This standardized residual is the y, the count, minus the fitted count that the model predicts, i.e. divided by the square root of that fitted value. That is the Poisson standard error. And then, just like you did before to get the estimate of the variance, you take that RSS. This is not RSS, this is the resid. We want to sum square of this guy divided by its degree of freedom. Degree of freedom is 2715 from the table earlier. Take the square root to get the variance, to get the standard error. There you go, 1.23. And this is the dispersion. This is the square root of that dispersion parameter. Okay, finally, let's look back at this table here. So what we've done is we run a straightforward regression assuming that the condition holds mean equals the variance, and it doesn't, so the standard errors are wrong. Then we did one which is robust to that, so it's still MLE, but it's Quasi-MLE, so it's robust to condition that the mean must be equal to the variance. And then some people say, well, why don't we also we should report alongside these standard errors, we should also report what they call the robust standard errors, robust to heteroscedasticity. That is because who's to say that our GLM assumption assumes that the variance, the conditional variance, is equal to this dispersion parameter multiplied by the conditional mean, right? That's the GLM assumption. Let's bring it up again. Where is that? I write that. Here. GLM assumption is this guy. Who's to say that needs to hold? You see, if you look at general statistics or econometrics, you'll see that we don't need this. We can kind of get by without this assumption at all, and that's where you get the robust standard error. So robust just basically means that it can withstand any violation of any kind of condition. So in large samples, people say that's probably the better one to go for, right? So how can we get that here? Well, just out of your own interest, we can get that by using what they call the sandwich estimator, because that is a general form turns out to be a general form for the variance. Turns out to look like, because it looks like the equation looks like a sandwich. To get that, we need to call up this sandwich package, and then what do? Then we can call up a consistent estimate that's robust to heteroscedasticity, and the form I'm using is White's consistent standard errors, which is for large samples. So here you go. Wow, it looks like a very because remember, this is a variance covariance matrix, So what we just need are just the diagonal elements. So for PCNV, that is 1.022 times 10 to the minus 2. But remember, that is the variance. So if we want a standard error, we want to take the square root of that. So if we take the square root of that guy, that's not no 1.023, say. This 1, 2, 3. Yep. 1, 2. Yep. Okay. We get a value of 0.1. All right. So if we look back at, just trace through my commands. Look back for the coefficient of PCNV. Okay. PCNV. Oh, not 0.1. Not 0.1. So some econometricians will say that in large samples don't bother too much because with the heteroscedasticity one, don't worry too much about heteroscedasticity because it won't make much. In practice there's very little difference between the standard errors given by the standard errors robust heteroscedasticity and the Quasi-MLE one. Okay, so there's a lot of issues there, but the main issue is that with a Poisson regression, the condition that the conditional variance being equal to the conditional mean is most likely not satisfied. So how you can get around that is just to use Quasi-MLE, because although MLE is consistent, the standard errors are wrong, and hence your t-test will be wrong. So just use a Quasi-MLE because that is both consistent and robust to departures of conditions for Poisson. One final point I'll raise also is that instead of the Poisson, some people then go instead for the negative binomial, because from construction, the negative binomial, the variance doesn't have to be equal to the mean. But hey, this is I've shown you that this is pretty much simple enough to run, so it's really up to you. You can have a try with the negative binomial as well, but this works perfectly fine. With the negative binomial, how that might arise is where you have say x, the random variable, which is conditionally Poisson, conditioned on lambda. So lambda is also allowed to be a random variable. Allow that parameter lambda to follow something like a gamma. So basically what you have is a mixture model, a Poisson gamma mixture. Then you will find that when you do the calculation that the distribution of that Poisson gamma is basically a negative binomial. And that's how I've learned it coming about. Alright, so well, there's loads there. I hope this has been useful.